So during the first talk, we developed tools that, if I'm okay, should help us in building deviation inequalities, concentration inequalities, for the kind of weird functions that we're supposed to meet in statistical learning theory and possibly also in statistical learning applications. So you were nice enough to believe me. I will now try to convince you that I'm not cheating, that those concentration inequalities do have something to say about well-known animals in learning, in statistical learning. So I will review a certain number of notions, of concepts that showed up in Bernard's talks and yesterday evening also, and that will show up again in Olivier's lectures next week, and possibly in Alex and others that I'm not now aware of. So, and those animals are mostly those concepts that help us to quantify the complexity, the richness of the function class we try to learn with. Okay, for example, the set of functions built from a certain kernel. Okay, so let's start with a warm-up, which is the fat shattering dimension or the DC dimension. Well, before I will recall certain notations, to fix things and to really to spot the kind of tools that we are now in our bag. So remember, the guy I'm looking for is always Z. Z exponent I or Z sub I are just two possible perturbations of Z, which I will use at my convenience, and at yours also. And I have two possible ways of monitoring the sensitivity, the lack of smoothness of the function Z. And these are my D plus and D, which are obtained that way. And remember that here the expectations is over the ghost variable, so the fixed prime I. Okay? And the two things, the two take-home messages of the two preceding talks were those red inequalities. The first one is the good old Elfenstein inequalities. 1980 or 1981. And we saw yesterday that we can actually, under some reasonable conditions, boost this Elfenstein inequality and bring it to the level of exponential models. So we may say something about exponential tails if we can understand the behavior of D plus. And we have analog behavior with respect to D, and so what remains to do now, because I guess random networks is not your favorite topic, is to go to learning theory, to the learning theory problem, and check whether we have something to say. So Bernard talked about fat shattering dimension, but we stick to the VC dimension. So in case you need, I will define the fat shattering dimension. So we have a certain function, real value, a set of real valued functions, a certain mesh, gamma, small positive real, and a sample. So remember that this is the shorthand for x1, x2, xn. And I would say that the fat shattering dimension at scale of gamma, should I say gamma?
Gamma?
Gamma. Gamma is okay. Thank you for adopting the French standard. And so this is the largest size of a subset of x1 and xn that is gamma shattered. So being gamma shattered, what does it mean? It means that whatever the sequence of signs I choose here, so think of the epsilon I are +1 or -1, I can find a function f in my favorite class such that f has the same sign as this ij as epsilon ij, and moreover, the product is larger than gamma. So the absolute value of f here is gamma. Gamma is something you should think of them as a margin in the supervector classification. And here Z, this is the size of the largest gamma shattered guy. Well, the VC dimension is a special case of this. You take gamma equal to 1, and your classifiers are assumed to be plus or minus 1,000. The gamma shattered, the one shattered set, is just a shattered set. And the size of the largest one shattered subset is just the VC dimension. So this quantity is a random variable in its own right. Maybe hard to compute, but actually I'm not very much in the practical side, so I don't care. 8 questions. How does it scale with the sample size? How does it behave? Is it something that will behave in an erratic manner and give you a nightmare? And from one sample to another will jump from 10 to 10,000? No. This is a well-behaved quantity. Why? Because being shattered is an hereditary property. If you, the sample, the set, are gamma shattered, any of your subsets is also gamma shattered. So this flat shattering dimension, this VC dimension, this is nothing but the largest cardinality of the subset satisfying some hereditary property. Just like being a packing in a set of intervals. So then we go back to the next slides from the preceding talk, or even before, and we see this is a case where if we choose Zi as the flat shattering dimension, when you remove the I guy in the sample, you have this nice separation that sum of Z minus Zi is smaller than Z. The increments are bounded by 1. So this is really a configuration function, a self-bounded function. And you may answer to all those questions about the related stability of the flat shattering dimension. And you get an Bernstein inequality for the flat shattering dimension, or for the VC dimension. These are stable quantities. It means that the average empirical VC dimension on a sample is very much like the typical VC dimension. If you want, maybe it's those concentration distances to go very far away from what you're really interested in, and you ask, ooh, what is the take-home message? I mean, concentration inequalities try to address the following question. Is the average rate behavior also something typical? If you want to figure out what could be an average behavior which is not so typical, think that you are playing in some kind of lottery. And say there are 100 participants in the lottery. There is the top price is 10,000 euros. And so, and there will be one winner. So the average gain is, say, 10,000 divided by 100, so that's 100 euros. What is a typical gain? It's very close to 0 euro. And with high probability, with high frequency, 99, probability 99 over 100, you win nothing. So if you have to pay, you even lost something. Okay. This is a case where this is a case of negated results in concentration of measures here. So here we're not playing lottery. This is well-being fun. So, but now we'll address something which is a little bit more sophisticated than the empirical VC dimension, which is what Bernard called the VC entropy. So, remember, maybe I don't use exactly the notation, so now you have a class of Boolean classifiers. And you define the trace of this class of classifiers on your sample. So this is a kind of number of way to separate sample in two different classes. And you present that with n-dimensional Boolean vectors. And the VC entropy, so this is still another entropy. We had the entropy for the concentration theory. Those who were familiar with information theory and large deviation may have spotted that it's highly related but different from the relative entropy or two-back information. And yet, another entropy, the Patrick-Chauvenet entropy, which is the binary logarithm of the size of the trace. We will play the same game again. We will define Z as this quantity, and Zi has the discrete entropy when you remove one guy from the sample. So this will decrease the VC entropy. Not very much indeed, or maybe not at all. No. Anyway, we are just projecting this vector along one dimension, pi point. What we have for free is this. And what we will get for G is that the condition on the increments, my favorite condition, which is this one. Sum over Z minus Ci less than Z. Why? Well, we already had two entropies. Why not the third one? So now we have a Bayesian force and information theory. So let's be a probability on any finite set. The Shannon entropy, which is the very entropy, 1948, of P, I will denote by H of P, is a sum over the support of P of minus Pi plus S2 of Pi. So there is a certain amount of folklore about the Shannon entropy, and among other things, we know that it is positive. Okay, none of Pi is negated. So we have no real choice. And a little convexity, this is homework, tells you that it is maximized when P is uniform over its support. So for a given support size, the uniform distribution maximizes the Shannon entropy. Now I will use the conventional notational abuse that is performed in information theory. I will compute the Shannon entropy of, I will define the Shannon entropy of the random variable and the Shannon entropy of its distribution. this allocates notation. And introduce another conditional entropy, say the conditional entropy of variable x with respect to y, as the expectation, where we take expectation over y, of the entropy of the conditional distribution of x with respect to y. This is, in the finite context where we did, it's perfectly defined and works perfectly well. Now, thing to remember is the chain rule, which tells you if you have the joint entropy of the entropy of the joint distribution of x and y, and then this is equal to the entropy of y plus the conditional entropy of x given y. And convexity strikes again, conditionally can only decrease entropy. So, okay. Now we have a magic thing, which is the hand inequality. Actually, this should be called the Loomis, Whitney, Shearer, Bombieri, Serre hand inequality, because all those people have discovered or rediscovered in the timeline of 30, 40 years this inequality. What does it tell? It tells us that if you consider a sequence of n random variables, which may or may not be independent, really doesn't care, and consider the entropy of obtained when you remove one of those random variables, well, you can use the chain rule that this inequality with the fact that conditioning may only decrease entropy, then use the chain rule again to get that. So if you're curious, and this hand inequality is some kind of weak isoperimetric inequality. And the good thing to remember about is that the entropy is something like the logarithms of a volume. There's an influential paper by Loomis and Whitney from 48 that gave a clean version of hand inequality in this respect. This one is from 1978. Now, well, the VC entropy, go back to our study. It can actually be considered at the entropy, the Shannon entropy of the uniform distribution over the trace. Okay? Remember here. We may redefine the uniform distribution over the trace, plug that into the definition of the Shannon entropy, and you will realize it. I'm not cheating. Very true. Okay. So, putting a uniform distribution over the trace is just as putting a uniform distribution over a subset of -1, 1 to the n, the two-point space. So, Z is Shannon entropy of this random vector. And Zi is the Shannon entropy of the projection of this random vector. The projection of this random vector may not be uniformly distributed over its supports. But that doesn't really hurt, because this can only decrease the entropy. So Zi is certainly not more than this one. Not, Zi is certainly not less than this one. So combining hand inequalities with those remarks, we get sum of Z minus Zi is less than Z. So we are again in the same game as we were before. So it's again what Emmanuel Rio called a self-bounded function. So then we push the button, find the right concentration inequality, and get that the VC entropy as a variance which is smaller than its expectation, and that we have Bernstein inequalities for it as well. And I'd like to comment things about that. Well, first, we shouldn't be too enthusiastic about it, because as pleasant as it may look, it may be very, very conservative. We know from October, from the 60s, that if you consider half spaces in the Euclidean space and a distribution on the examples that absolutely continuous with respect to the Lebesgue measure, then with probability 1, we come out with a sample which is in general position. And then you can compute the VC entropy using a formula. So in that case, VC entropy is not only concentrated, it's morally, or with probability 1, a constant. And from all the results by, not so old results, by Eduardo Zonta, this may be true for many class of classifiers defined by sigmoidal neural networks, and possibly for some classes coming out from SVMs. But anyway, I think we capture something there, because the result holds whatever the set of classifiers we consider. So it's not the VC entropy of a certain class of classifiers over a certain distribution. It's some kind of general property that we have. And actually, something that we call combinatorial entropies. If you look, go back to our packing problems from the first lecture, and now I may ask the questions. How does the logarithms of the number of packings behave? I know that the size of the largest packing is well behaved. I may also ask, so how many packings can I find? And there are exponentially many, so I take a log to have something at the right scale and ask, does it concentrate or not? Well, you can carry out exactly the same reasoning and realize that you also get the Bernstein inequality for those. So, now I will revisit a little bit the role of the VC entropy. This will be an opportunity to try to relate those concepts of capacity to the real problem, which is usually the discrepancy between the empirical classification error and the expected classification error of our classifiers. So I will give us somewhat different version of the symmetrization, a version which is not exactly the same as Bernard, not in the light of the Lapin-Chabanek's papers, but rather in the light of the ordinary empirical processes. So, remember, at first glance, the quantity we would like to control is this one. So this is a training error. So pay attention, Bernard told me this might have been confusing. I'm not normalizing. So I'm not dividing by n, because when you are doing concentration, things look better. So it's this one. But I will rearrange this expectation and say I'd like to introduce ghost samples. So instead of taking n times the expectation, I will take the sum of identical terms, where I explicitly say that I'm taking independent copies. Then guess what happened? I play Jensen inequality again. Because I have a soup here, I have an absolute value, so everything is convex as it should be. I am in the position to play Jensen. But then I have a product distribution over the first sample and the prime sample. So that in sophisticated language, I say that I'm using Houdini's theorem. Well, those two quantities are distributed in the same way. So we have actually completely symmetrized the random vector, the random process we are looking about. So this is symmetrization in the good old style of Boucheron. So it's very respected. But then it doesn't hurt to add some Rademacher variables. So this epsilon random variables take value +1, -1 with probability 1/2, and they are completely independent from those two expectations. I put that it's just as exchanging the role of xi and x prime r. Doesn't hurt. But then the sum over the red people and the sum over the blue people behave exactly the same way. So I may apply what triangle inequality and separate those two expectations are exactly the same. Then I invoke Houdini again, and I put the expectation over the epsilon, the Rademacher variable inside, and I get this expression where the blue quantity should be considered as something which is conditional with respect to the sample. And this is, for that reason, that it is called a conditional Rademacher average, defined over the class F. And so, just as in Bernard symmetrization, we should pay attention to the fact that this only depends on the trace of F over the sample. So, we have a relation between the expected quantity. This is one of the first time I talked about expected quantities. And this quantity. And I want to stress the fact that this relation is both general and tight, because if we were more courageous, we could prove that it goes in the other way. So this is small. This is smaller than 2 times this. We are within a ratio of 4, and even what we should usually have in learning theory, we should be happy with. So now, my time goes on. If we were really courageous, we would carry this computation. I will not. I'd like to underline the red inequality. So what does this red inequality tell us? It tells us that the conditional Rademacher average is not larger than this quantity, which is the square root of the number of people that counts. Remember that this only depends, I mean, the soup here is actually a max. We could as well consider a max over the trace of F on the sample, and this is finite. Okay. Plus times the soup over all people in the trace. I mean, this is actually the largest vector in the trace. So now figure out what does it mean. Suppose that our sample is shattered. So then the log of the trace is just n. No, yeah. So we've got something which is square root of n, and here we have a guy which is equal to n. So this quantity is n. It means that our bound on the discrepancy between empirical and effective error is as bad as it could be. It's, if you normalize by n, it's, yeah.
As bad as it could be times 4.
Times
4 or 2.
Times 2 or 4. So it means it's trivial. It means that if you can shatter this set using f, you're really in a bad shape. Forget about learning theory. But I mean, if F is a nice class, it is a VC class with VC dimension D, and D is smaller than N, then this grows like G times log N. After taking the log. Then, actually, you may play that on a subset of the class. It's actually a very good thing to do. And guess what happens if you consider people who behave well on the sample, so which have a small empirical error. And then we get the term which may be square root of d log n times square root of something which is much smaller than n. And then it becomes non-trivial. Actually, this is a getting out with this line of design. Now Z is it's not the VC entropy. It's the discrepancy between empirical and effective errors. When you take F, which may or may not be the whole class, just a small subset of a big class. Taking that line of reasoning where, I mean, you use Cauchy's parts here, and then use the fact that this is nicely upper-bounded by that, you get this relation between Z, this quantity, which is nicely concentrated around its mean. That means that on a sample, you can make an estimation of this quantity and with high confidence think that this is very close to this expected value. And this is an empirical performance of a guide like that. And this line of reasoning, which when you're well equipped is not that hard to follow, is at the basis of something that Olivier will talk about next week, and which is very trendy now in learning theory. It's a kind of localization procedures, and that are supposed to help you in determining from the data, using possibly hard computations, what is the capacity of your set of classifiers with respect to the sampling distribution that you don't know, and even more, give you with high confidence, tight, not trivial, upper bounds on the generalization error of the rule you have selected. So now I would like to go a little bit further in this direction and go one step further in historical development. So I think getting that the fat shattering dimension was, or the VC dimensions are nicely concentrated, is something that could have been stated in 95. If Michel Calacan had been interested in those questions, he could have had a footnote in one of his big papers and pointed that. The VC entropy came a little bit later, in 99, 2000, and it was partly due to the fact that we had this understanding of D and D plus, and it was, some say, more user-friendly than the complex distance physics. And actually, it took some time, and it should not have, understand that the conditional Rademacher averages, which have been a constant subject of concern for people interested in concentration inequalities, should also behave nicely. If you look at the book by Van der Vaart and Fender, you'll see that those conditional Rademacher inequalities, which play an important role in empirical process theory, enjoyed since 1990 deviation inequalities from above, and it is really non-trivial to prove using control by Q point, one of the paragraphs spreadsheet. But this is Q without rift, and this is not the thing that is listed in the normal place. And then it turns out that the Rademacher complexity, which is the first thing we should look at when trying to understand the capacity, the richness of a class of classifiers or functions at large, also enjoys the property of self-bounded functions. It concentrates nicely around its mean, and it enjoys some kind of Bernstein inequality. So here, the game is still Zi is defined by removing a guy from the sample and using, say, triangle inequality. You can check that Z minus Zi is positive and smaller than 1, and that sum of Z minus Zi is smaller than Z. Yet again, this gives you the Bernstein inequality. So then ask yourself, what does it mean if we have a VC class? That determining this class with VC dimension and we're bounded by D. It means that if you do some nice usage of the union bound and of chaining arguments, you will be able to check that the expectation of the Rademacher complexity is of order square root of the VC dimension multiplied by n. It's not larger than this. And what you got from Effelstein inequality and from our concentration inequality, that typical deviations are significantly smaller, and they're of order at most n to the 1/4. So it's much more interesting than what you can get by using a bounded difference inequality, which would tell you that the variance is smaller than something times n, and that typical deviations are both of order square root of n. It would just tell you typical deviations are of the same order at worst than the average value. So I think it's a progress. Well, now, 10 minutes more, we can deal with suprema of empirical processes. Because actually, that's what we were first interested in. Remember that my last Z was this one. This one is just a suprema of an empirical process, the centered empirical process. Well, let's first take it positive, because it's much easier, and we'll play again this familiar game. We assume that it's not only positive, but bounded. And guess what? Zi is just taken by removing the I person in the sample and still maximize it. Again, the same conditions. By, so we have a self-bounded functional, and Bernstein inequality comes from 3. Actually, and if you take Bernoulli random variables, so there's only one guy in your class, and it's x value 1 or 0, you can check that they're not that far from true. Actually, if the xi's are not identically distributed, let's say, have success probabilities, is that some remains smaller than a certain mu, then it's, so the larger n I take, okay, I will take the probability that xi for 1 equal to mu over n. Then there is something called the law of rare events that tell you that the distribution of, say, this will converge to the Poisson distribution with mean mu. And in that case, those inequalities are tight. So you can exhibit construction where this inequality, those couple of inequalities, tell you exactly the truth. Do not prove them. Anyway, if you are not in such a nice setting, if you are, say, in a binomial setting where the xi's are identically distributed, success probability P, then you lose something. And it should not be exactly at the same tail bounds. And you can recover the binomial behavior by using devices designed by Emmanuel. And actually, in order to do that, you need to design another family of modified logarithmic Sobolev inequalities. So it's a surprise for this. But it may be worth doing. So now, an example of a supremum of positive bounded empirical processes that show up in SVM analysis. I think it's an idea from Yasandola, Melo, Tellini, and Shaw-Taylor last year. Consider the Gram matrix. You have a linear kernel, theta comes from Euclidean space, and the Gram matrix at indexes I and j is just the dot product between example xi and example xj. And there is a lot of concern around the spectrum of this Gram matrix. It seems to be a quantity to look at. In particular, to look at this first R eigenvalues when yes, Nello Cristianini and John Shaw-Taylor had the idea that it can be represented as a supremum of a positive bounded empirical process if the distribution of the xi's has bounded support. Actually, we should define phi p as a projection on the orthogonal projection on a subspace V. Some of the first eigenvalues, the first R largest eigenvalues, may be represented as the sup over all subspaces of dimension R of sum over I. There's a big difference on this slide. Of what? The square norm of the orthogonal projection of xi on V. This is a supremum of positive bounded empirical process in its own right. So, from what I said previously, this satisfies non-scale inequalities. Okay. And that comes from free. I have absolutely no idea about the mean behavior of that. I know it's, in a certain sense, relatively stable. So, let me again stress the fact that I'm trying to separate the analysis of average behavior and the analysis of deviations. This is two different businesses, and this is an example. And before the close, let's talk about the real business, suprema of bounded empirical processes, and maybe positive or negative. So these are the people that show up when you are centering. It's quite important. Then I don't give the detail, but if you play the V plus game, so using a ghost copy and looking in the way it disturbs your people, you end up with the following up or down for V plus. So here there's a part that depends exclusively on the sample. And here is a part, well actually I should put the sum here again, didn't do my physics, which is something deterministic. And that's the nice part, that's the ugly part. But the ugly part is not that ugly. It's actually the thing we have dealt with just in the slide before. Yeah? It's a suprema of a positive bounded empirical process. So we know something about its log Laplace transform. Actually, I've used the previous result to give this not so sexy bound, but that's fine. Okay? And then I will play my exponential Einstein inequality, which tells me that the log Laplace of my z is related to this log Laplace. And this leads us, after a little bit work, and this business that relates this expression, which is often called the strong variance of my empirical process, with something which is my z, and this is a weak variance, times n. So I end up with this, which is quite beautiful, and plugging in the exponential Einstein, I find that I come up with that. So I may play with theta, with lambda, making optimization, and then get a headache. So then I may recommend another recipe for controlling the empirical process. Is to use the official concentration inequality for suprema of bounded empirical processes. Well, this is something that grew up at the end of the preceding century, starting with papers by Talleyrand, who did that with his own wizardry, and then Michel Ledoux came with it. And this is where he popularized the entropy method. And this has been further refined by Pascal Massard and Emmanuel Rio and the guy there at the end of the room. So now the official world record is 48. And it tells you that if you use this as a variance estimate for your empirical processes, this Z, you can use a tail down in this user-friendly off-the-shelf form. So for small a's, typical definitions, you will get something which is like a Gaussian behavior with a pseudo variance for p. And for large deviation, you will get exponential tails, which depends more or less on the upper bound you have on the increments, on the maximum value that f of xi is allowed to take. Okay? So, this is the end of the third lecture. For those who wish, I think we may come back in, say, a quarter of an hour. So it means 10 past 5. Okay.